Hello, my name is Gary. I'm from Section 6, Group 5. Today, I will represent my team to explain our AC to DC power supply designed for the SKEE 1073 Electronic Devices and Circuits Assignment 1. In this video, we will break down the design and function of a basis AC to DC power supply using a bridge rectifier. We will cover the core functional stages, the transformer, rectifier, filter, and voltage regulator, explaining how AC is converted into a stable and clean DC output. We have specifically chosen to build a bridge full-wave rectifier, which is arranged as shown in the diagram. This is because full-wave rectification utilizes both the positive and negative halves of the AC input signal, while half-wave rectification only uses one half of the AC cycle. This means that half the input power is wasted in a half-wave design. Additionally, the output from full-wave rectification has less ripple compared to half-wave rectification, making it easier to filter into a steady DC voltage. Our circuit consists of several key components. An AC voltage source acts as our AC power supply, generating a sine wave with a peak voltage of 100 V at 50 Hz. This voltage source is connected to the step-down transformer. Since LT-Spice does not have a built-in transformer component, we will model it using two inductors, L1 and L2 with inductance of 10 Henry and 0.33 Henry respectively. Then the rectification is handled by 4 regular silicon diodes with a forward voltage drop of 0.7 V, forming the bridge rectifier. We also included two resistors, R1 and RL, to allow us to measure potential differences at specific nodes in the circuit and also to limit current through certain parts of the circuit. For filtering, we use a 1000 microfarad polarized capacitor, and for the voltage regulation, we use a Zener diode with a Zener voltage of 12 volts. Additionally, waveform viewer in LT-Spice are employed throughout the experiment for waveform visualization and voltage measurements. After building the circuit, I will now explain the working principle of the circuit. Firstly, for the transformer part, the 100 V peak voltage from the AC voltage source is too high for our desired usage. Hence, we must use a step-down transformer to reduce the voltage. In order to model a transformer using inductors, we will use a specific formula to get the step-down ratio, and L1 will act as the primary coil, L2 will act as the secondary coil. Most importantly, we must write a SPICE directive, K L1 L2 1. This directive tells SPICE to couple L1 and L2 with perfect magnetic coupling. K is the keyword for the magnetic coupling, and L1 and L2 are the primary and secondary coils respectively. And 1 is the coefficient of coupling. 1 means perfect coupling with 100% efficiency. Moving on to the next stage, rectification. This configuration enables full-wave rectification. During the positive half cycle of the AC input, diodes D1 and D2 are forward biased and conduct current through the load. During the negative half cycle, diodes D3 and D4 become forward biased and allow current to flow in the same direction through the load. This results in a unidirectional but pulsating DC output. We will now continue on the explanation of the filtering stage. The filtering stage is implemented by connecting a large capacitor between the rectified output and ground. The capacitor charges during voltage peaks and discharges during voltage dips, smoothing out the fluctuations. The higher the capacitance, the more effective the filtering, as it reduces ripple in the voltage significantly. We can clearly see that the waveform with a higher capacitance capacitor shows a much smoother DC output. For the final regulation stage, we use a Zener diode connected in reverse bias across the load. A series resistor R1 is placed between the filtered DC output and the Zener diode plus load combination. The Zener diode maintains a stable voltage by entering breakdown mode when the voltage exceeds its rated breakdown value of 12 V. The series resistor drops the excess voltage and limits the current, thereby protecting the zener diode. The current is shared between the zener and the load, and the voltage across the load remains constant, resulting in our final regulated DC output. Last but not least, we will now run the simulation. In order to inspect the rectified but unfiltered waveform, we must remove the components after the rectifier, which means removing the filter, R1, zener diode, and RL. Then we measure the voltage at node C to see the rectified waveform. This is because the bridge rectifier is in parallel with the capacitor. Hence, if we directly measure node C without removing any components, we will only see the filtered voltage waveform, but not the rectified and pre-filtered waveform. Here you will see that the AC waveform have been rectified. Both halves of the waveform are now positive. Moving to the filter stage where we can connect back all the components, the waveform still contains some ripple, but it is significantly smoothed out. Finally, in the regulator stage, the waveform becomes mostly flat and steady. Only a little bit of fluctuation is present, which is acceptable, producing a clean and constant DC voltage output. In conclusion, an AC to DC power supply using a bridge rectifier follows these main functional stages. Transformer, which reduces or steps down the AC voltage to a lower and desired voltage. Bridge rectifier converts the AC input into a pulsating DC output. Filter smooths the pulsating signal by reducing voltage ripple, and regulator ensures a clean, stable and constant DC output for electronic devices. So this is the end of our video, and thank you.